Hi guys, I'm Jeremy. I'm one of the ENGG1200 tutors, and I'm also one of the electronics tutors for ENGG1200, and we've had a lot of the same questions coming from some Project C groups, so I thought I'd do a video and try and explain a whole bunch of stuff that might be relevant to your project and hopefully give you a bit of a kickstart so you can get it done. Righto, so let's start by taking a look at the problem we have. So really the thing we want to look at is the strain gauge. So a strain gauge can be modeled as a resistor. Except the only thing about this resistor is that it changes its resistance with respect to strain. So the way we normally deal with a resistor that changes its resistance is using a thing called a Wheatstone bridge. Now there's one thing we need to talk about before we get to that, and it's called a voltage divider. So if we have our V in, that goes into one resistor, goes into another resistor, and goes to ground, then the voltage at this point is a function of V in, R1, and R2. So let's call this V out. So in the case of a resistor divider, it will be V out equals R2, if I remember correctly, on R1 plus R2 multiplied by V in. So that's fairly straightforward, but you might be thinking, well, how the hell does that help me? So we're getting there. So now imagine that we have two resistor dividers. So we'll get rid of this guy. Okay, so we have our V in. We're going to just draw it in a diamond because it's a bit easier to work with. Right. So this will be, let's say, R1, R2, R3, and R4. Now, it should be pretty obvious that we have one voltage divider on this side, one voltage divider on this side. So if we knew the values of R1 and R2, we can use this formula from before to work out the voltage here. We'll call this V1. And using these two guys, we can work out the voltage here. We'll call it V2. So, still it may not be obvious why we want to do this, but the trick is that this guy here is our strain gauge. So if we consider that these are all going to be constant, then we also assume that R3 equals R4. So these are the same. Then if you put in the maths, you'll find that V2 comes out to be V in on 2. Now this is not necessarily true for this side because this guy can change his resistance. But what we can say is that we still know how to calculate the voltage out at V1, but that our quantity of interest will be V1 minus V2. So it'll be the difference in the volts from here to the volts at this reference point. So our signal is really a subtraction of two voltages. So this is where the differential or difference amplifier comes in. So if we have, and this is a simplified version, but if our signal is between V1 and V2, V1, V2, then if we have something that can find V1 minus V2, and that comes as V out, then we found the signal we want. So that's basically the point of a differential amplifier. It finds the differential between two voltages and makes that its output. Now there are lots of different kinds of differential amplifiers, and they all have this special thing called common mode rejection ratio. Basically, if you have a very high common mode rejection ratio, the output will be almost perfectly V1 minus V2. Now, unfortunately, because they're built in the real world and nothing's ever that perfect, you generally get very close to V1 minus V2. You might have other little factors like plus 10 to the negative 7 V1 plus 10 to the negative 12 V2. So this is because it's in the real world. Now, that's not necessarily such a bad thing, because 10 to the negative 7 is pretty small. 10 to the negative 12 is horrendously small. So if V1 and V2, if this is 1 volt and that's 5 volts, then we'll get negative 4 volts out, plus this tiny little fraction that really we don't have to worry about. So if our common mode rejection ratio is high, which they are in instrumentation amps, then we don't really need to worry about this other jazz. And there'll also be, you know, plus a bunch of things like noise, and there'll be thermal noise, and there'll be noise induced from, you know, TV signals and all that other rubbish. But if we have a high enough common mode rejection ratio, and if the signal, if this has as much noise as this one, then it will all hopefully get subtracted out pretty well, and we'll get V out equals out. Okay, but the problem might be that these guys are, well, the difference between them is not very big, and so while we'll still get the signal we want, it could be on the order of, you know, 2 millivolts, let's say. Now, if you hook up an oscilloscope to nothing, and I'll show you this later, it'll actually look, well, the output will look something like this on a small scale. So this could be as high as, this would be 0 volts. This could be as high as, say, 20 millivolts. So that means there's signal existing in your wires without you connecting anything, and that's because we have radio waves and all sorts of stuff going through the air, and it just naturally gets picked up by things that conduct. So we need to, if our signal is 2 millivolts, well, it might only just shift it up like a little tiny bit, and you know, that can be pretty hard to find. So we've got to do other stuff to get this 2 millivolts to where we want it. So in the context of the project, what we really want is we want 3 volts for no input, that's a U, and we want 12 volts just before jut, of course, just before breakage. Right, so what you need to do is work out the voltage that's going to be V1 minus V2 that's going to come out of your instrumentation amplifier. So let's say in our case it is going to be 2 millivolts. Okay, so really 2 millivolts we want to come out for something very large. So let's say 2 millivolts was our breaking point. That is a very, very small voltage to break at. But anyway, so what we really want to do is make 2 millivolts map to 12 volts. And we want 0 volts out to map to 3 volts. So there's two things we need to think about. We need to think about the gradient. So as our strain starts to get from 0 towards 2, as it starts to get bigger, we need to start going from 3 to 12. And there'll be a defined gradient. So if we go up by 1 millivolt, how much should this go up by? That's the gradient. And the thing we also need to think about is the voltage offset. So if we want to make 0 volts into 3 volts, we can't just do it by multiplication. We have to add some volts on. So the two things we want to look at to do this are, we have gain blocks. We'll just draw it like that with a G. And then we have a summing block like that. So what we want to do is we want to take our signal in and make it into the signal we want. So the first thing we have to do is, if we have a 0 volt signal, we're gonna have to add 3 volts no matter what, which means that we don't really want to go up to 12 volts anymore before that, but really what we want is a 0 to 9 volt output before we add 3 volts on. So it'll be, our signal comes in, something, then we have a summing block which will be plus 3, and then we have our output. So now we've got to work out what can make our signal 0 to 9 volts inside here. So we know that if we put 0 in and we multiply it by something, then we get 0 out. So that's good. We don't need to do any more of this addition stuff. So what we need to do to get it up to 9 volts is realize that if we have 2 millivolts, we want to get it to 9 volts, then there's some factor that if we go 2 times 10 to the negative 3, which is millivolts, times G equals 9 volts. So really, we want to find out G, and I'll leave that one up to you. But essentially, we want to make this block a gain block, so it multiplies the voltage in by G, and then we have our plus 3. So it will look like, so signal coming in, we'll have a G block, and that will be times G, which is this value over here. Then we go into our summing block, which will be plus 3, and then we have our output. So it seems pretty abstract at this point, but now is where I start to show you some actual electronics. So we realize that we need a gain block, and we realize that we need a summing block, but we don't really know how to build these in real life. So there are these important people in electrical engineering called applications engineers, and they work for the big companies like Texas Instruments, Analog Devices, plenty of them, and all they do is think about ways to help you use their products. Now you might think that that's kind of for marketers, but no, these guys actually build good products and they're very useful to you. So they bring out these documents, and they're called, well, the first two are application notes, and this one in the back is a data sheet. But these are 3 of probably my favorite documents for getting this sort of stuff done. So I'm just going to take you through them really quickly to show you how I would do something like this. So the first one I want to show you is the Application Note 31 op-amp circuit collection. So basically this is a book full of circuit designs that translate these blocks into things you can actually build. So this one was produced by Texas Instruments. They bought National Semiconductor, so it was originally made by National Semiconductor, but doesn't really matter. So this guy here is what we call an op-amp, and if I dig around here I might have a few to show you. No, that's not it. Here we are. So this is an op-amp. This is a big op-amp actually. So this has got in it two of these weird looking triangle things. And I can show you that to you because the other thing that these companies produce is a thing called a data sheet. So you might think that this, let's see if we can get that better. You might think that this is like a really simple thing, you know, it's just got 8 little pieces of wire coming out of it, a black piece of plastic. This is all the information that Texas Instruments give you if you buy this chip. So it's all sorts of characterizations and experiments and where you can use it, and seriously anything under the sun. If you want to use this in a satellite, you can buy a special part. If you want to use it in a race car, you can buy a special part. Or even stuff like, let's see if I can find it. So they have all mechanical drawings of all the different ways you can get the part, and it goes on forever and ever. Nope, apparently it's not there. Have one last look. There we go. So this is if you want to buy the part in a big reel. It has the exact dimensions of all the reel, not just the part, but the reel. And if you want to buy it in a box, it even has all the dimensions of the box so that you can program a robot to open the box, pick the part up, and then put it on your circuit board. So in here, you just take one of these guys, put it in that place, and then you can build a circuit that works. So I've gone and built these two circuits, so I'll get my breadboard set up and we can have a look at what they do. Okay, so the first thing that we got to do before we look at the circuit, I may have forgotten, is look at how to build the circuit. So this is what that op-amp looks like, this one right here. And you can tell that pin 1 is there because of this little shiny dot. Okay, so this 1 out pin is this first silver pin, 1 in minus is the next one, 1 in plus, next one, VCC minus, next one. So what we need to do is, for every single part, connect its VCC minus and its VCC plus. Now op-amps are kind of special in that they need both a negative voltage and a positive voltage. Now negative voltage is not the same as negative on a battery or a ground on your power supply. Now negative voltage is actually a negative voltage. So if you to think about it another way, if you put the voltage across a resistor, the negative voltage would flow backwards. So it's not quite the same deal, but it doesn't really matter because the labs at uni will have negative and positive voltage supplies. So I may get round to showing you how to set that up later, but otherwise just ask one of the tutors in the labs. So after you've connected this one to 12 volts and after you've connected this one to minus 12 volts, we can actually look at the circuit we're building. So this here is our op-amp. You can see it's got a minus, it's got a plus, it's got an output. Don't worry about these numbers so much because this isn't the op amp we're using. We're using a TL072. But the same thing applies. Output minus plus. So if we look back on here really quickly, output minus plus, output minus plus. So this actually has two of these triangles in it. So if we want to connect this circuit up, what we need to do is have our V in, get an R1, connect R1 into the minus, so that will be 1 minus, pin 2 on the little black chip. Then we take ground, hook it up to the plus on the chip, which will be pin 3, and then you fix your page up. And then we have minus into a resistor and then into the output. So if we look back at this, we go from minus through a resistor and then into the output. And then the signal we're interested in is V out. Now if you look down here, it tells you what block this is. Now generally an amplifier, what it does is it multiplies the input signal by something to get the output signal. And funnily enough, that's the formula for it. So it's the resistance of R2 divided by the resistance of R1, and then you multiply V in by that and make it negative, and you'll get your V out. So this is our gain block, except it has a minus in the front, which is kind of annoying. But the trouble is that in real life we can't just build the things that we imagine. Well, we can't just build them straight away. We've got to fiddle around with a bit. There is no get a new block in Simulink. You've got to actually make it yourself. So there's plenty of other ways you can amplify things. This one here is an inverting amplifier. So, a non-inverting amplifier. So what that means is this minus that was over here is gone. Now it changed the gain equation slightly, so you may have to fiddle with the resistor values to get the one you want. But there's still some factor times V in equals V out. So same deal. We go from our negative through a resistor into the minus. So we go from ground through a resistor into the minus, pin 2. Now we go from the minus through a resistor to the output. So we go from the minus, pin 2, through a resistor to the output, pin 1. And then on this plus guy, we put in the voltage that we want to see. So in the plus, we just attach the voltage that we want to see come out of the output. Simple enough. So when you build it, it looks like this. So this one here I put together is an inverting amplifier. So first of all, notice that there's pin 1. So it might be a bit hard to see, but I'll see if I can zoom in. Ooh, is it gonna like me? Nope, I guess not. That's as good as we're gonna do. So if you remember back to the data sheet, pin 1 is our output. We don't even need to remember, it's right here. So we want to go from V in into a resistor into pin 2. So I'm pretending that this row is my V in, this is the resistor we're going through, and we're all the way into pin 2. Now down here we want to go from the minus through a resistor into pin 1. So we've got from pin 2 here, this resistor, we go through it and we're into pin 1. Now the other thing we have to do is connect this guy to ground, and I've done that because we've got our ground coming in here, goes down this blue row all the way down, through this wire into this blue row, then all the way back up into here, and then this connects into pin 3. Sorry, yes, that is pin 3, which is the minus. Sorry, it's the plus. So to go through that again, this is ground. Ground goes into pin 3. Pin 3 is the plus, so we've built our circuit. Now I also built the non-inverting amplifier. So we go, first of all, ground through a resistor to minus. Minus is pin 2. So we've got ground through a resistor into pin 2, which is over here. Now we go from pin 2 through here into the output, which is pin 1. So back here we've got pin 2 through a resistor into pin 1, and see the little shiny thing here means pin 1. So then the other thing we have to do is V in goes into pin 3. We haven't connected that yet, and we've got to connect our output. Okay, so now we can start to look at our circuit. So what we need to do first is give it a signal in, give it a signal out. So the first thing we want to do is signal in. Now I've attached a signal in to this yellow wire. This comes from my function generator. We've got lots of function generators in the lab, and basically the point of the function generator is to generate a mathematical function where the output is a voltage. So for a sine wave, it'll go up and down, up and down, up and down, up and down forever. And basically you can put these mathematical functions into your circuits to see if they're doing what you think. So I've hooked this guy up to my oscilloscope, and we want to look at the output, which is on pin 1. So I'm just going to go ahead and put this into pin 1. Right, so now I'm going to change views so you can see my oscilloscope, but I won't touch this. This will be exactly the same. Righto, so here's my oscilloscope. It's actually got 2 channels, so this is just like your scope in Simulink, but the real one. It's got 2 channels. They're both on, and they're both being drawn here. Now the reason you can't really see them is not because I haven't zoomed in, even though I will a little bit more, but it's because there's not actually any voltage across them. Now if we turn this one way up, you'll see that there's heaps of signal, and I'm not sure if you can tell, but this is on a 2 millivolt scale. So that means that each one of these grid spacings is 2 millivolts. So this is, in terms of volts, this is a very small signal, but if your strain gauge output was 2 millivolts, you can see how it could kind of get lost in there. So this is why we use the differential amplifier. But let me put it back down to 500 millivolts division, that's a bit better. So now, just to quickly show you, this is my function generator. It's got a bunch of keys. You can change the mathematical function you want to put in, you can change the frequency, the voltage, whatever you want. In fact, right now I'm going to change my sine wave to 1 volt peak to peak, which means the sine wave will go up half a volt, down half a volt, or sorry, from the top to bottom will be 1 volt, and then it'll go up 1 volt, down 1 volt, keep going forever and ever and ever at 1 kilohertz. I don't know if that's really visible. Yeah, maybe just a little. And then all you can do on these things is change the frequency, and it's very easy to test your circuits at all sorts of different frequencies. But anyway, let's test the circuit we have now. So I'm going to switch the output of my function generator on, and you can see now we have this funky signal on our oscilloscope. So I've hooked up this channel directly to the output of my function generator. So this isn't going through any amplifier, this is just the signal that's coming out. And if I zoom this one in a bit, just give me 1 second. It's telling us that V peak to peak is pretty much 1 volt. I'd say that's within error. But here's the interesting thing. 2.6, let's call it 2.65 volts is coming out of our amplifier. And you'll notice that it's actually been turned negative. So this is the negative sign on the gain equation at work. So as this becomes more positive, this guy becomes more negative. And as this one becomes more positive, this one becomes more negative. Now, we'll go through later and calculate the exact gain, but just remember 2.65 and 1 volt. Okay, so this one here, this is my non-inverting amplifier. So remember, this one didn't have a negative in the gain equation. So when we see the sine waves, they should be exactly the same, just with a different amplitude. So we'll hook this one up just like we did before. So this yellow one is our input signal, and our input signal, according to this, should go into V in, which is the plus, and the plus, if you remember the data sheet, is pin 3. So put it in there. So that's now connected to pin 3 on our breadboard. Now the other thing we want to do is look at the output on our oscilloscope. So we get our green wire, this one, and we want it to go into the output, which is pin 1. So I'm just going to put that one in there. Make sure these aren't touching because that will stuff the circuit up. Okay, so I'm going to switch back to the oscilloscope. Won't change this. It's going to be hooked up the same way and we'll see what it does. Okay, so we're back on the oscilloscope, and as you can see it's doing some weird stuff with the noise. You'll actually find if you measure this, it will be 50 Hertz at a sine wave. Let's see if I can see it. It's a pretty poor sine wave, but this is actually the 50 Hertz of all the power lines around here, just going through the air and going inside all my signals on the circuit, on the breadboard. So just keep in mind that noise is a real problem. But anyway, let's turn the function generator on and look at what our amplifier does. And I'll fix up this time scale. So you'll notice now that as this one gets more positive, this one also gets more positive. So we now have a non-inverting amplifier. All we get is whatever value here multiplied by something becomes this value up here. Now if we look down here, we still have about 1 volt in, but we have we'll call it 3.7 coming out at the top. So the difference between these two is 3.7 volts. The difference between these two is 1 volt. Now we can use this sort of system to make the gain blocks in our device, but because we don't want to just randomly have some gain, we need to use the mathematical formula to work the gain out. Alright, so let's work out the gain values that we got for those two circuits. So the first thing we need to know about gain is, if we want to calculate it from an experiment, it's always V out on V in equals G. Now there are different variations of this, but it always comes down to this. So for our first amplifier, the inverting amplifier, we already know it's negative. So V out, we worked out, was 2.65 volts, I think, on 1 volt that we put in. And it's very convenient that we put in 1 volt, hint hint, because it means our gain is just negative 2.65. So the same thing goes for the second one that we found. So it will be 3.7, I think it was, on 1 equals 3.7. So our gain stage that we built in the second case would have a G of 3.7 volts. And the first one, the inverting amplifier, would have a G of negative 2.65 volts. So we don't actually have to do all this experimentally though. We can work them out using the formulas in my favorite book. So coming back here, if we look down here, we have negative R2 on R1 V in. So really our G value, if we took V in on the other side, we'd have V out over V in, which is gain. So our G equals negative R2 on R1. Now I can tell you, because I built it, that the values I put in were R2 equals, oh, you can't see that, R2 equals 12K, and just as a side note, whenever we write K we really mean 10 to the 3, so 12,000 ohms, and R1 equals 4.7K ohms. So if we were to do R2 on R1 equals 12,000 on 4,700. So I'll just type that in my calculator, just because I don't trust my own brain. We've got 4700. It's 2.55. So this will be our G value. Now that's quite similar, oh, and we know it's negative as well, so negatives go in there. So that's pretty similar to this one. So this is the one we found experimentally, this is the one we calculated. So let's do the same thing for our non-inverting amplifier, the second one we built. Now I'll get the book and see if you can see that. We have R1 plus R2 divided by R1 is our gain. So G equals R1 plus R2 divided by R1. Now I use the same values as before in the same configuration. So if we have 4700 plus 12,700, that will give us a gain value of, back to the calculator, 3.55 times, which is about the same as 3.7. So now the thing we need to talk about is, well, why weren't they the same? Because that's really important. You don't want to do all this maths and then find out that you're completely wrong. So the thing is that the resistors you buy are not exactly 12 kilo ohm, or they're not exactly 4.7K. You actually buy them under tolerance codes. So the ones I have here are 12K plus minus 2%. Because really, you can never buy a perfect resistor, because they'd have to machine it perfectly, and that's impossible. So the same thing goes for my 4.7K plus minus 2%. Now you can buy resistors that have this percentage really, really low, but of course as this percentage gets low they start to become a lot more expensive. Now I would have paid perhaps a cent or two for these resistors, but if you were to buy, let's say, 0.001% resistors, you would probably be paying $100 for one. So In fact, maybe more. But the point is, generally we try and design circuits to use these ones because it's 2 cents versus $200. Now, just to make you aware before we move on from amplifiers, is that this book here, which you should be able to find the link to, I'll put it up, does not just have 2 amplifiers in it. There's at least 4 on this page, but really it's got pages and pages and pages, and they really go for ages. And in fact, there's a diagram in here, and I probably won't be able to find it because there's so many of them. I won't bother. But there's actually a diagram in here for an instrumentation amplifier, which is the thing you got in the little package. And so it's got, basically inside there, it's got a bunch of these triangle dudes, op amps, and a bunch of resistors that are configured to increase the common mode rejection ratio, which is what we talked about earlier. So the other thing I want to point out are these offset voltage adjustment amplifiers. So what they let you do is, instead of just doing V out equals G times V in, you can actually do, we don't want this, you do G times V in plus V, let's call it X, right? And you can calculate what you're going to add on to. Now, if you remember from the start, we needed something that was G times V in plus 3, right? So if you can build an amplifier, an offset trimming amplifier, they're also called summing amplifiers, then we can add this on, and then we have our G and our summing block. So make sure you have a look at this book here. It's very useful. I use documents like this all the time to build circuits, so it's good if you can find them, good if you can read them. Now, the last thing we need to talk about, and probably the most difficult thing to talk about, is filters. Now, if you think about a signal going into an oscilloscope, it's probably, let's think of it as a sine wave, right? So a sine wave has frequency. So that means if you take this point, there's a time between them, and the cycle will repeat many times per second. So if this were to repeat once per second, this time interval would be 1. If this were to repeat twice a second, then this time interval will be half. And if it was to repeat 4 times a second, then this time interval would be 1/4. So that means that t equals 1, t equals 0.5, t equals 0.25. So this is how long it takes for it to get this far. But if it were to repeat twice, then if this was 1 second, then this would have to be half a second. So we have another way of talking about it, which is cycles per second, or hertz. And calculating hertz from this period, we call it, is really easy. It's just F equals 1 on T. So for this case, F would be 2. For this case, F would be 4. And so this is 4 cycles per second, or 0.25 seconds as a period. So if we were to, and this is going to be kind of weird, but let's think about it a different way. So we have this graph, and on this side we have how much, and on this graph we have frequency. Sorry, on this axis. So if we know that this sine wave, well, because it repeats and it's a sine wave, it's got to have a frequency. So if our frequency was 1 hertz, this guy, then if we were to think about it on here, then we would have a mark. If this was frequency, we'd have a mark at 1 Hertz. And this, we'd have maybe, let's say, a line there. So this is how much of this 1 Hertz sine wave we have. So in real life, we don't really think about it as how much. We think about it, well, there's lots of ways, but we're going to think about it in volts. So this would be 1 volt. Right? So let's think about it differently. Let's say that now we have t equals 0.5, so the frequency will be 2 Hertz. So now this would go away, but maybe we have one here, Hertz, and it would go up to 1 volt because we're pretending that it's 1 volt peak to peak. So you can do this for any sine wave, and you can plot its frequency against its volts. So that's a pretty simple concept, but it starts to get weird if I told you that any signal can actually be represented by frequencies of a sine wave. So if I were to have a voltage signal, so this will be time, this will be volt. If I were to have a signal that looks like this, so this is what we call a square wave, and it goes on forever and ever and ever and ever. You can actually represent this as lots of frequencies of sine waves. In fact, to represent a square wave you need infinity frequencies. Now, this is really starting to stretch things, but now if we go and we call this the frequency domain, a square wave actually looks like this. So if this was a 1 Hertz square wave, so it repeats once every second, we would have what we call a fundamental 1 Hertz, and then you actually get successively smaller ones that go all the way. Ooh, that wasn't small enough, but you get the point. We have lots and lots of sine waves, different frequencies, and then if you join them all together you get this. So there's a bunch of maths that you can put any mathematical function into and you'll get the frequency version. Now this is important to us because our signal from the strain gauge is very slow. So it's not going to change very fast at all because it depends on how hard you're pushing down on the piece of metal. So we're not really interested in all these sine waves up here. They're just like useless information, and if we have them, they'll get in the way. Now if you remember on my oscilloscope, it was going like blah. Now you can actually, in the same way that you can model this as a bunch of sine waves, you can model this as a bunch of sine waves. So, and I'm making this up completely, but it could be something like that. So what we want to do is have a circuit that can say, well, I'm not really that interested in anything past this guy. So it would be nice if we could just like delete these, and then all we have left over is this one thing, which will actually just be nice clean sine wave of, let's say, 1 Hertz. So if the signal we want is going to be on the order of 1 Hertz, so it's not going to be changing or cycling very fast, then we want a circuit that can delete this other stuff and turn this into the nice signal that we want. So we get rid of all the noise or the frequencies that we don't want. Now, there are a lot of circuits that do this because this is a really big problem in electronics, and we call them filters. So this here is, and this is probably my favorite application note ever. This is Filter Design in 30 Seconds by Bruce Carter from Texas Instruments. Again, Texas Instruments, I really like what they do. But if you look here, and I'll zoom in, this is the same thing that we had before. So there's an axis with frequency on it, but see, this one here has gain. So what a filter does is it has this curve, and then any frequency along it is multiplied by the gain value. So down here, if we assume that this line here was, let's get my pointer. So this line here, if we assume that's 1 Hertz, if we put a 1 Hertz signal, just a sine wave, into our filter, then it will be, and now this is in decibels, so don't get confused, but this will do nothing to a 1 Hertz sine wave. So it will multiply it by 1. And it will be the same as we go along. Now let's say this is here. Let's say this is 10 Hertz. So now, as we get to 10 Hertz, it's starting to bend down. So it's going to actually multiply 10 Hertz by, at this point, I can tell you because I've done this before, at this point it will multiply the 10 Hertz sine wave by 0.707. And then as we go down, 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 let's say this here was 100 Hertz. So now any 100 Hertz signals we put through, they're going to get pretty small. This is going to multiply them by half. And then as we get further and further, it's going to multiply them by very, very small values, so they'll effectively go away. Now, this is what we want, right? So we had this, and we wanted to delete these guys. So we can't actually just completely get rid of them, but what we can do is just try and make them smaller. So we have these filter circuits. Now, this one here is called a low pass filter, because low frequencies are passed and high frequencies are blocked. So the same thing goes here, but this is a high pass filter. So low frequencies we multiply by very small numbers, but then as we get to higher frequencies we multiply them by 1, so nothing happens to them, we keep them. So low frequencies are blocked, high frequencies are passed. So now the reason we use this book is because it does everything for us. Now, I really like the way he wrote this, so I'm just going to try and get it. So it even says, this document is intended for designers that do not have the time to check filter theory in old college textbooks. Sound like anyone? This is like looking in the back of the textbook for an answer. So, why this document is good, and there are some more filters you can build, but let's say we wanted to build a low pass filter. So we want to keep our low frequencies and get rid of our high frequencies. All you have to do is go to page 3, and then it says, oh look, there's our triangle op amp again. This is a capacitor, this is a resistor, this is a resistor, this is a capacitor. That's where your signal goes in, that's where your signal comes out. So then it even has a design procedure. So first pick C1. I usually start at 100 nanofarads. Calculate C1. C2 equals C1 times 2. So 200 nanofarads. Calculate R1 and R2 equals this big guy. So in here, the thing we're interested in is the frequency. So if you remember back here, we had this point which was the cutoff frequency. So this is where we start to cut off frequencies. And this is the frequency they're referring to in the formula. So if we wanted to build a filter that started to get rid of stuff after 1 Hertz, we would put 1 in here. Or if we wanted to get rid of it after 1 megahertz, well, it would be 1 times 10 to the negative 6. Sorry, 10 to the 6 goes in here. And then it gives you the value, and that is what you use for R1 and R2. And then you're done. You just go back to the circuit, build it, put in your R1, put in your R2, put in your C2, put in your C1, put the op amp in, connect the supply, and you're done. So that will build you a filter that goes like this. So when you put a sine wave through a filter, you'll get a sine wave back out. But if you were to put our old friend the square wave in, which remember is infinity sine waves of different frequencies, if we were to have a very, very good filter, so volts, and this is frequency, so if we have the frequencies in our square wave looking like this, and then we want to go filter afterwards, the filter, then signal might look like this. Because what we did is we multiplied this guy by a very small value, so let's say 10 to the negative 9, and then we multiplied this guy by a very small value times 10 to the negative 11, because remember the curve, and I'll get a different pen just to show this, the curve went something like this. So all the frequencies along here get destroyed. Now in real life your filter would probably not be that good. May look something more like this. But keep in mind that we're still multiplying these things, and this would be multiply them by 1. So we're still multiplying them by 0.7, 0.6, 0.5, 0.4. So they would get a lot smaller. They would be something like, and then down here you probably wouldn't even see them. But let's pretend we have this red filter that's really, really good, and it gets all other frequencies to go away. Well, we can't even measure them. They're still there, but they're so small we can't measure them. There's just this one left. And then that means what's coming out of our filter, if we go back and look at the time, this is V, this is time, will be a perfect sine wave. Even though that's not a perfect sine wave. So, back in terms of the strain gauge project, we might have a signal coming out of an instrumentation amp that's going like, and this would be 0 volts, and this would be time volts. So really the value of strain we want is this value in the middle. We don't actually care about all this flipping and crazy stuff. And this is actually, coming back to here, all these high frequencies, because it's cycling really fast. So when we put a filter on, if our filter's really good and it multiplies all these higher frequencies by really small numbers, then what we can get out is so that's time, it's volts, and it might be something more like which, you tell me, if that was on the same scale, which one of these is better for what you want to do. So that's why we want to use filters. Now the interesting thing is we can't just whack a filter on the end, because, and it looks like I've run out of paper, so I'll do it on the, okay, I'll do it on the back anyway. Now we can't go G, then sum, and then filter, because what we did was we multiplied all of the frequencies in the noisy part, the stuff that we don't want, we already multiplied them by like 1,000. So now when it gets to here, well, we've just had a bunch of noise that we could have got rid of. So what we normally do is we have a G down here that is quite small. So this is where we get the signal we want. This is the instrumentation amplifier. Then it goes into a filter. And then we have another G, let's say times 100. Then we have the summing stage. So what this does is, this does the minusing. This is our difference amplifier. We get out a little bit of a signal. It'll be multiplied by 10, so maybe 20 millivolts. Then if it's all like crazy, this filter will hopefully turn it into, well, it'll still have a little bit in it, but it'll be a pretty straight line. It'll be a pretty constant voltage. Then we belt that up with a lot of gain, so it'll be a straight line just way up here. And then we add on 3 volts extra. So this way we've still got 1,000 times gain. It's still times 10 and then times 100, but we've multiplied all the higher frequencies, all this stuff, by lots of little numbers. So really the frequency we want will be multiplied by 10, multiplied by 1, multiplied by 100, which is 1,000. But then the frequencies that we don't want will be multiplied by 10, multiplied by 10 to the negative, I don't know, 15, and then multiplied by 100. That is most certainly not 1,000. And so that way we get a much cleaner signal out on this side. Now you might ask, well, if you still do this, you get 1,000 times same thing. Should still be the same thing, but unfortunately these blocks themselves actually introduce more noise. In fact, if you do all the gain here, you're going to be amplifying lots of noise that this guy generates itself. So that's why we have to keep this one low, maybe 10, and then do the filtering straight away. Now it's possible to put this one up a bit more, maybe 100 if you really have to, but you want to make this gain stage as small as possible. And so the last thing to talk about is picking a frequency for this filter. Now if you think about how fast the strain gauge is going to be loaded, it's not very fast compared to 1 megahertz. So 1 megahertz, if we use our formula from before, will be 1 on 1 times 10 to the 6 now equals 0.000, well, you get the idea. So the time it takes to cycle is really fast. So if we had a 1 megahertz signal, we want to get rid of that. And if you think about it, really we don't even want frequencies that are as high as 1000 hertz, 100 hertz, or even 10 hertz. I mean, really we want to start at getting all the signals below 1 hertz. And even lower if better, maybe 0.1 hertz. So back to our filter calculation document. In this formula we'd probably want something that was maybe 1 or 0.1, because our strain value is not going to change very quickly, but we know our noise values are very high frequency, so they're going to be changing heaps and we want to get rid of them completely. Yeah, so that was a lot of theory, but hopefully some of it makes sense. Alright, so there's one last thing that I forgot to mention. So now that we've gone through all these amplifiers and we know what frequencies are, you might be thinking that our original voltage divider so this is R1, R2, this is V out, and this one changes with strain. So you might be thinking, if we can put the strain one here and we know this one, can't we just work out V out when this guy changes? And you'd be right, but the problem is noise. So this strain gauge does not change its resistance very much. So this might be 120 ohms and this might be 119.998 ohms. Now if you were to put that in your resistor divider formula, you would find out the V out is very, 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 very small. And if you remember looking at the oscilloscope, the noise is, you know, it's small, but it's actually relative to a signal like that quite big. So really, all you'd get maybe, let's say, 1 millivolt. But if the noise is 20 millivolts, it's going to be kind of hard to find this one. So the way we solve this problem is by comparing it against a reference. So we go back to our Wheatstone bridge, like so. So this is our one that changes, and so we look at the difference between these two. Now the interesting thing in here is that the difference isn't really that, it's not that much different to here. The difference between these two is still going to be really tiny, but this exploits a property that we call, see if you can remember, on mode noise. So the idea is that because in real life, geometrically and physically, these two resistor dividers are very close to each other, so that any noise that exists in this conductor is probably going to be the same as the noise in here. Now, if we know that this noise is the same and this noise is the same, we can have, if we call this V1, V2, so V1 will be V1 signal plus V1 noise. V2 will be V2 signal plus V2 noise. But we're saying that these two are the same because they're very close on our breadboard, so any like radio waves that hit this part will probably hit this part the same. So when we do V1 minus V2, we actually do V1S plus V noise plus minus V2S minus V noise. And so look, this signal that we didn't want, this signal that's generated by all sorts of crazy stuff in the environment, we now have plus that and minus that. So it cancels out, and what we have left over with is V1 signal minus V2 signal. And so that is common mode rejection. The noise is common to both parts, so we reject it using the common mode rejection powers of a differential amplifier. So that was all I really wanted to show you guys for now. It was kind of a brain dump, sorry, but I hope some of the information can help you do a lot better. I'll put the links for those 3 documents up on Blackboard, and hopefully with this video. So if you have any questions, don't think I'm the only one that you can ask. All of the tutors in the electronics labs are really good at this stuff, so just make sure you ask them.